In this video, we're going to look at how to solve a multiple vector problem using the analytical method. There's already a video solving this exact problem using the graphical method, and I'll link to that video in the description of this video so you can compare two methods. And so you have an example of a problem solved by the graphical method and the analytical method. So in this problem, we have four vectors which are outlined on the screen just now. In each case, we're going to resolve the vectors into their horizontal, so that's our east-west direction, and vertical, that's our north-south direction. And we'll use the analytical method to combine all of these horizontal and vertical components to find the overall resultant vector. We'll also, having found the resultant, be able to state what the equilibrium is for this system. That is the vector we need to add to this system to make it at static equilibrium. Let's take each vector in turn, and to keep us right, I'm going to number each of our vectors, and I'm going to draw a little space diagram as well, just to make it nice and clear which way all our vectors are pointing. So we'll put in a quick set of axes here to represent our compass directions. So there we are. We'll draw the vectors in freehand to save a little bit of time. So first of all, we have a 12 km/h vector acting due north, and that means that it's along the north axis. So try and draw it slightly better than that. Along the north axis. So it's really in line with that, and I'll draw a little arrowhead there, and that's 12 km/h. We've got a second vector, 15 kilometers at 30 degrees east of north. That means starting at north, we rotate 30 degrees clockwise to get our second vector, which is going to be here. This is going to be 15 kilometers per hour. We can indicate that this angle in here is 30 degrees. We've got a third vector, which is at 20 kilometers per hour at 40 degrees east of south. So that means pointing south, we're going to move anti-clockwise towards the east. Roughly about here, we'll have a vector. This is not obviously a scale diagram, so I'm just drawing these things in to get a rough proportion of where they're heading, and a bit of a reminder to make sure that all of my calculations are pointing in the right direction. And lastly, we have a 12 km/h vector due south. So I'm at 12 km/h. So these are our four vectors. So we're going to take each vector in turn and find the horizontal and vertical components, and that will be the first stage of the problem. So let's start with vector 1. I should just make a wee north sign at the top there. East, west, south. And we'll use the convention where vertical north is positive and south is negative, and horizontal east is positive and west is negative. So vector 1, the force, so a vector, let's get this right. Velocity, so we use Vn. We won't use that, we use V1, so vertical velocity for vector 1, and that's simply going to be equal to 12 km/h. And we can leave it like that because we know positive means north in this case. And we know that it's a vector that's pointing vertically upwards. That means VH1 is going to be equal to 0 km/h. So that's an easy one. Vector 2 is something we have to do some calculations for. So if we draw vector 2 in here by itself, we have a 15 kilometer per hour vector. It's 30 degrees to the vertical line, which means it must be 60 degrees to the horizontal line. And you can choose to use either angle here. We can create a triangle using the 30-degree angle or using the 60-degree angle. Both of these are fine. We just need to make sure we're using the right part of trig. But what I'll do is I'll use a 60-degree angle here because it looks more like what we usually do in this type of problem. So let's draw in our horizontal and vertical components. So we're going to have VH2 here, the horizontal velocity of vector 2, and we're going to have VV2, the vertical velocity component of vector 2, and we're going to use trig in order to find this. If we want to find the vertical component, first of all, well, we can recognise that this is the right angle triangle. The value 15 is the value of the hypotenuse, and the vertical component is opposite our 60-degree angle. So we can write sine of 60 degrees, because that uses opposite and hypotenuse, is equal to the vertical velocity, the opposite, divided by 15 hypotenuse. The vertical velocity component of vector 2 is 15 times sine 60 degrees. And that's 12.99. So effectively, to one decimal place, certainly 13, you can say 13.0 to be accurate, 13.0 kilometers per hour. And this means that we could work out the same way, but it's going to mean the cos 60 is going to be the adjacent of the hypotenuse. In this case, the adjacent is the horizontal component divided by 15. So the horizontal component is going to be 15 times cos 60. And cos 60 is equal to exactly 1/2, simply 7.5 kilometers per hour. That's vector 2 resolved. So let's look at vector 3 now. So vector 3 acts down the way at an angle of 40 degrees from the vertical line, and it has a value of 20 kilometers per hour. So in this case, we're going to use the angle we're given and just remind ourselves about being careful with trig. So we'll have a vector acting down the way, which is the vertical velocity of vector 3, and we've got a vector acting across the way to the right, to the east, which is the horizontal velocity of vector 3. Now the reason I'm saying to be careful here is if we look at this angle, vertical components adjacent to this angle of 40 degrees, not opposite it. So we actually have to check using SOHCAHTOA that we want to use cos to find the vertical. And the reason it's different is because we normally compare angles to horizontal. We could have taken an angle of 50 degrees up here, and then we'd have had sine and cos in the way that's commonly found in these problems. But we want to show that we do it based on what trig tells us, not just what we think is going to happen. So in this case, we're going to have cos of 40 degrees is equal to the adjacent side, which this time is the vertical component, divided by the hypotenuse. So here, our vertical velocity is going to be 20 times cos 40 degrees. And this gives us 15.3 kilometers per hour. But here we have to be careful because this is heading downwards. So we can either write 15.3 kilometers south, or we could give it a negative. We could say this is equal to negative kilometers per hour. Or you might prefer north and south. Let's stick with the negative though. So we should state this like this. We're not saying 15.3 equal to minus 15.3. We're saying this vector specifically is negative because it's heading down the way in our diagram. Now to find the vertical component, for the horizontal component, we'll use sine for this time. So sine 40 is equal to the opposite in this triangle, which is our horizontal component, divided by the hypotenuse. So the horizontal component of vector 3 is 20 times sine 40 degrees. And that's equal to 12.9. One decimal place, kilometers per hour. And that leaves us with the vector 4. Now, vector 4 is a nice, easy one to deal with. It's 12 kilometers per hour acting towards the south. So the vertical velocity of vector 4 is going to be minus 12 kilometers per hour, because minus indicates south in this case. And the horizontal component of vector 4 is going to be 0 kilometers per hour. And so we've resolved all of our vectors into vertical and horizontal components. The next stage of this question is to find the overall horizontal velocity and the overall vertical velocity that come from these vectors. So to find VV is going to be the sum of VV1 plus VV2 plus VV3 plus VV4, all of our vertical velocities. The VV1 was 12, VV2 was 13.0, VV3 was, well, take away that plus, it was minus 15.3, and VV4 was minus 12. And if we add all of those up, we're left with minus 2.3 kilometers per hour, 2.3 kilometers per hour heading south. The same for our horizontal velocities. If we add all of these up and we're conscious of the signs, we'll get an overall horizontal velocity. And actually in this case, we either have zeros in the case of the first and fourth vector, or we have positive values. So 7.5 plus 12.9 for VHC plus 0, which means we're going to have 20.4 kilometers per hour as our horizontal velocity. So far we have now taken all of our vectors and effectively turned them into just two vectors, one in the vertical direction and one in the horizontal direction. So how do we deal with these? Well, we draw another diagram, this time with just these two vectors, in the same way we'd have solved, began to solve the graphical problem. So we'll draw our vertical vector this way, representing minus 2.3 kilometers per hour. And we'll draw a vector along this way in the positive direction, representing 20.4 kilometers per hour. And again, this isn't a scaled diagram, it's just to illustrate what we're trying to work out. And our resultant vector is going to be, I'll put it in red here, is going to be this line here. So we find the size of this resultant vector by using Pythagoras, because r squared is going to equal to 2.3 squared. We don't have to use the negative here, and even if we did, it wouldn't make a difference mathematically. It's just the length of the sides, plus 20.4 squared. So r is equal to the square root of 2.3 squared plus 20.4 squared. I'll put this into calculus just now, but we should be expecting an answer that's bigger than 20.4 squared. I mean, that will be correct because it's the hypotenuse, it'll be the longest side. But it's a good common sense check that if it doesn't come out bigger than 20.4, something has gone wrong in your calculation. And it actually comes out at 20.5 kilometers per hour to one decimal place. And that's not always surprising when one side is much bigger than the other. It's quite close to the value of the bigger side. So we've found the size of the resultant. That's our resultant vector, 20.5 kilometers per hour. The last thing to do is to calculate the angle the resultant's acting at. Now, the angle we're going to be interested in here is the angle from the horizontal, but the one we're going to calculate is this angle x here, because we can use our trigonometry in order to find this angle. I suppose we could just leave it as angle x. I'll talk about that when we get to how we could express the answer. So we found the size of the resultant, 20.5 kilometers per hour. Now let's find its direction. So tan of x, because we have the length of the two sides we worked out in the previous part, which are opposite and adjacent to this. Opposite this angle is our horizontal component, and adjacent to it is our vertical component. That means that x degrees is equal to inverse tan of 20.4 divided by 2.3. Now you may wish to calculate this beforehand, but it can save some rounding and working out if we put it straight into our calculators. And the angle we get here is 83.6 degrees. So we could say, at this point, I should have said this, we could say the resultant is 20.5 kilometers per hour, and we could say it's 83.6 degrees east of south, which means from the south we're rotating around 83.6 degrees, or we could subtract that from 90 and we could find out the angle below the horizontal, or we could have said 90 minus 83.6 degrees, which is 6.4 degrees below horizontal, or indeed 6.4 degrees south from east, depending how you want to express it. But as long as it's clear in your answer which angle you've calculated to show the direction, then you've successfully answered the question. And that's the full analytical method that's required to solve a problem like this. As I said at the beginning, in the description of this video, there'll be a link to how to solve it graphically. The one difference, one additional thing we're going to say here that's different from the graphical method, I want to say something about the equilibrium. So the equilibrium in any vector problem is a vector that's the same size as the resultant. So we can immediately say the equilibrium is 20.5 kilometers per hour, and it's acting in the opposite direction to the resultant. So if the resultant is 83.6 degrees east of south, that means that the resultant will be 83.6 degrees west of north. And if that's harder to visualize, I'll quickly draw that on a little diagram here. If this is our resultant, which is very close to east, and this angle here is 83.6, then our equilibrium is the same size, or imagine this is the same size, acting in completely opposite direction, and it's this angle here, it's 83.6 in this case. So that's what our equilibrium is. So in any question we have to find the equilibrium, you can immediately say how big it is. It's the same size as the resultant, and just be careful about giving the opposite direction. Obviously something nice and easy, like the resultant is going east when the equilibrium is going west. But this is the angle that the equilibrium will take, which is the complete opposite of the resultant. And that would conclude a question like this.